In this example, we are going to look at example 2 on page 80 of your workbook. And this is another example of a sequence, okay, which we talked about in a previous example, but this time the sequence is given to us in the form of a formula. Okay, and let's kind of read through the first part of this example together. So suppose that the population of fish in a lake after n years is modeled by the formula Pn, and you can see the formula in front of you. Okay, so here's a sequence where the input values n represent years, and what's coming out of our sequence are actually fish populations. Okay, and this time the data is also presented to us graphically in the graph that you see over here to the right. Okay, so if we look at part A, they're asking us to actually do some calculating, okay, to see if we can figure out what the value of our sequence are, what the values of our sequence are for a few specific values. Okay, and let's start with the first number on our list, the P0 that you're looking at here. How would we calculate that? Okay, well, basically, it's just like a function. We would go up to the formula that we were given with the problem and just plug in 0 for every value of n. Okay, so I'm going to do that. Just take every n and replace it with a 0. Okay, whoops, I just hit the wrong button. Okay, sorry about that. Okay, so continuing with this, we're just plugging in a 0 for every n. Okay, and there's what our formula looks like. All right, and we know that e to the 0 is just 1. Okay, so if we do that calculation, this kind of simplifies down to 1002 over 3 plus 164. That's something that you can put into your calculator, and what's going to come out of that calculation is just a nice round number of 6. Okay, so we've just figured out then that at the beginning, after 0 years have passed, we're just getting 6 fish in the lake. Think of that as a starting population, if you like. Okay, we can do that for any value of n. So the next number on our list is P1. Let's calculate that. Okay, so it's going to look exactly the same as what we just did, just that we're going to plug in a 1 for all of our n's. Okay, and this time the numbers aren't quite as nice, but that's still something that you can put into your calculator and get a number out. This time, if you do all of that, here's what you're going to find. Okay, a number of 15.8, so our population has grown a little bit. Okay, you can kind of see that all the calculations after this are going to be similar. We're just going to keep plugging in different values for n each time, and we're generating a list of numbers, okay, which is how we defined a sequence. So what I'd like to do is to kind of make a table of the numbers that we get, that we're getting here. Okay, so we're plugging in values of n, which represent years, and we are getting out populations, Pn, in units of fish, and we can start our table by just putting in the numbers that we calculated above. So when n is 0, we got 6 fish. When n was 1, we got 15.8 fish roughly. Okay, and you could continue. I'm just going to show you what would happen if you plugged some more numbers in here. And you're welcome to pause the recording if you want to and maybe calculate some of these numbers yourself. Okay, but here are the next few values. So when n is 2, you're going to get 39.8. When n is 3, 89.7, and so on. Let's do one more. 166.9. Okay, now they also ask us, what do these numbers mean in the context of this problem? Okay, well, our table kind of tells us, because we can look at the units and see that they represent numbers of fish. Okay, so think of these numbers that are coming out as just being approximations of the number of fish in the pond after a certain amount of time. Okay, let's write that down. Okay, notice we use the word approximation because some of our numbers are not round numbers. It doesn't really make sense, for example, to talk about 39.8 fish, but according to our model, that's our approximation, so we would probably round to 40 in that case. Okay, now that's the end of what they asked us in Part A here. I want to point out Part B, the top of the next page, asks a very interesting question. Okay, does the sequence Pn converge? And if so, to what value? Okay, and you might be able to take a guess, okay, at the answer to this question just by looking at the data that we have so far. Okay, our numbers, 6, 15.8, 39.8, 89.7, they seem to be growing really quickly. And you can kind of see that behavior in the graph up here in the upper right-hand corner. Our graph seems to be getting steeper and steeper. And so if I had to guess, I would probably say that this sequence is diverging. It's going off to infinity. We're not approaching a number, which is what we would need to have happen if we wanted to get convergence. Okay, but I'm going to just slide the page up a little bit here. What would happen if we plugged a few more values into this function? Okay, well, I'm going to draw a graph, very rough graph, just showing you what would happen if we added some data points here. Okay, bear with me. This is going to take a minute to put all this together. We're kind of doing this from scratch. Okay, and I'll warn you, this is going to be a very rough graph that we construct here. Hopefully accurate enough, though, to kind of get the idea of what's going on. Okay, we'll go up to a value of 8 months in this case. Okay, now if we plot the points that we already have very roughly, okay, here's what we're going to see. Okay, and I apologize, this pen doesn't like to plot points very well. Okay, so our first few data points look like that. That's that pattern that we saw on the previous page where it looks like the populations are just getting bigger and bigger and bigger. Something kind of interesting happens if we continue, though, with the data. Okay, so again, I'm just going to plot very roughly here. What you can see and notice that after we hit that number of n equals 4, it appears that that rate of growth is slowing down. So I look at the second graph and I'm not so sure anymore as to whether this population goes off to infinity or maybe approaches a number. It looks possible that our population might be leveling off. So the question is, how do we decide for sure what's going on here? Okay, well, fortunately, there's a mathematical way to settle this, to decide whether this sequence converges. We can do it by just taking a limit of the sequence using the notation that we talked about in a previous example. All right, so what we're going to do is we are going to calculate the limit as n goes to infinity of our population. Okay, we'll start that calculation. Okay, just with the formula that they gave us for the population. Okay, so I'm just recopying the formula from the previous page here. And we're just interested in what happens as n gets bigger and bigger and bigger here. And the thing to notice, this is going to take us back to Calculus 1 for a minute. Ask yourself what's happening to the numerator and to the denominator of this fraction. Okay, as n gets really, really big, 1002 times e to the n, that's going to go off to infinity. It's going to get bigger and bigger. And in the bottom, the same thing is going to happen. 3e to the n plus 164, that also gets really, really big. So we've got a fraction where the numerator and the denominator are both going to infinity. You might remember that this is a situation where we can apply L'Hopital's rule to calculate a limit. All right, so let's do that together here. L'Hopital's rule, and this is kind of going back to Calculus 1. To do that, you just take the numerator and the denominator separately and take the derivative of both of those. Okay, so I'm going to start with the numerator, 1002 e to the n. The derivative of e to the n stays the same, so we're just going to get the same thing all over again. Okay, and when we take the derivative in the bottom, the 3e to the n is going to stay the same, but the 164 is going to go away. Its derivative is 0. Okay, so we come down to just the limit of 1002 e to the n over 3e to the n. Okay, and notice, now that that plus 164 is away, we can actually cancel here. The e to the n's go away, and we come down to just a limit of a ratio of two numbers, 1002 over 3, and that's something that we can calculate. Right, you can double check me on your calculator. That gives us an answer of 334, and so what we have just proven is that this sequence actually does approach a finite number. Okay, you can think of 334 as the number of fish, the population of fish in the lake that we approach as time goes on. Okay, so just to summarize this, we could say that the sequence converges to 334, which is just a way of saying that our fish population approaches 334 in the long run.